So much of advanced calculus deals with trig functions and representing things with polar coordinates and spherical, and so we need to be more and more comfortable with trig, especially if there's the potential for us to go further in the calculus. So we need to use trig identities. They make our lives simpler. So let's relate it to something. Let's wrap our brain around why that is and how we should be looking for them. Let's suppose, well, let's not suppose, I think we know that there's 100 pennies in a dollar, 5 pennies in a nickel, and so on. Let's suppose I'm cleaning out my ashtray or my whatever that thing is in my car. I drive a minivan. Anyways, but so I'm cleaning it out. I got 500 pennies, I got 60 dimes, I got 16 quarters. I'm going to put it in a bank earning 10% interest in my dreams, and I want to know how much money I'm going to make the next year. Well, I think what I'm really saying is that I have 500 pennies, that's $5. I have 60 dimes, that's $6, and I have 16 quarters, that's $4. So if I add $5 plus the $6 plus the $4, then what I'm saying is I got $15. And if I take $15 and I put it in the bank, earning 10% interest, then I'm going to get $1.50 in interest the next year. But by making a substitution, by saying that every 100 pennies would give me $1, it makes this a lot easier. I have 5 $1. I have $6. I have $4 because I can replace 10 dimes with $1, etc. So I think you get that idea without us taking too much time there. We go to the unit circle. The reason it's called the unit circle is because the radius is 1. By making the radius 1, it makes the hypotenuse of all these little right triangles that we put in there equal 1. And so every point along the unit circle is 1 unit away from the origin, and every point can be labeled as cosine theta, sine theta, or cosine x, sine x. So by the Pythagorean theorem, it must be that this side squared plus this side squared adds up to be the 1. So we have the Pythagorean identity. Well, what this guy allows us to do is, based on that, we can say, hey, let's divide every term on both sides by sine squared, and we'll end up with this. So this gives us another trig identity, that the cotangent squared of theta equals this, or that you could replace cotangent squared plus 1 with cosecant squared. So the Pythagorean identity, when we divide both sides by sine squared, leads us to another important relationship. Likewise, divide both sides by cosine squared, and you get a relationship between tangent squared and secant squared. So all a person really has to do to memorize these 3 trig identities is to start with the Pythagorean identity and then recognize how each of these then would come from that. Then we go to the double angle formula. The main form of the double angle formula that we should start with is that if you take the cosine squared minus the sine squared, that's equivalent to the cosine of twice this angle. And so this is important if we realize that based on the Pythagorean identity, we could get the other 2 forms for the double angle. If we say that we could replace sine squared with 1 minus cosine squared, because we know that sine squared x plus cosine squared x equals 1, so sine squared would have to equal 1 minus cosine squared x. So if we make that replacement and we do the math, then we say, oh, this is how we get that the double angle for cosine is also equivalent to this guy right here. And then likewise, if we start again with that form of the double angle for cosine, and this time we replace cosine squared with its equivalent based on the Pythagorean identity, we get this form of the double angle. And again, the further we go into calculus, when we get to integration, some of these things become more and more beneficial to us. So what do we have? All we really have to do is memorize this guy, cosine squared plus sine squared is equal to 1. And this guy, the difference of those 2 is equal to the double angle of cosine. And then from that, we can get 2 more important trig identities. So memorize this guy and that guy. And then as time goes along, if you can memorize these, that's fine. But anytime you're working a problem and you see some of these other representations and you think, my life would be easier if I could replace it with something more succinct, then by all means do it. The only other one you have to add to these, so really I would argue just the third one that you have to memorize, is the double angle formula for sine, which is 2 times the sine of x times the cosine of x. So if we could memorize that guy along with those two, we'd be in good shape. So these will serve us well. If you get to this, if we say, hey, find the derivative, dy dx, when we get to this problem, we say, oh, you know what? There's the subtraction, the difference of cosine and sine squared. That's the double angle formula for cosine. So we can replace this with the cosine of double this angle, so that's 10x, and that's pretty easy to differentiate. We can use the chain rule, so we're taking the function of a function. So first we would take the derivative of cosine of this, which is negative sine of that angle, and then we'd multiply it by the derivative of the angle, which is 10. So in the end, the derivative of y with respect to x would be negative 10 sine of 10x. But similarly, we see this function over here that we got to differentiate that guy. And it's like, ooh, subtle difference. When it's subtraction, double angle for cosine. But when it's addition, we know that anytime you take the cosine squared of any angle plus the sine squared of any angle, that equals 1. And the derivative of any constant is equal to 0. That's like a Staples commercial. That was easy. So here we go to this one. Now we see this, and it looks kind of messy. If we didn't recognize that we could replace this with the double angle for sine, then we'd have to be using the product rule and the chain rule amongst all that, and that's just too messy. But we recognize that we have 2 times the sine of some angle times the cosine of the exact same angle. So we say, all right, we can simplify this by saying that all this would be the sine of double whatever that common angle was. So we can go to that right there, and we'll be able to use again the chain rule on that and get that the derivative of y with respect to x would be the derivative of the sine of that angle multiplied by the derivative of the function inside, so it'd just be 8 cosine of 8x. And then if we see this, we say, that looks kind of messy. I wish there was something we could do to clean that up. And then we realize, oh yeah, tangent squared, that's where we got the secant squared and the cotangent. This is the secant squared thing. That's it. This comes from the Pythagorean identity. So then our next step would be to say, oh, okay, I can replace that guy with secant squared of x times cosine cubed of x. And we don't stop there because there's more simplifying we can do. We say, okay, that's good, but maybe we can clean this up more, because otherwise we're looking at a product rule right now. So again, you always want to simplify before you have to do the dirty work of the derivative. So we realize secant squared of x is really 1 over the cosine squared of x. And we're going to multiply that by the cosine cubed of x. So this guy cancels with 2 of those guys. So what we're left with is y equals the cosine of x. And we know that the derivative of that is just negative sine of x. So these puppies, along with the double angle formula for sine, that the sine of 2x is equal to 2 times the sine of x times the cosine of x, can save us a whole lot of time when we're taking derivatives of functions that involve trig. So we need to memorize 3 of these puppies. We need to memorize, in my opinion, others would disagree with me, but we would need to memorize this guy, and from it, you can get those. We need to memorize this guy, and from it, you can get those. And we need to memorize this guy. And in the process of memorizing those, if you also end up memorizing these guys, more power to you. But again, you can also see that tangent squared plus 1 is equal to secant squared. And so we see that there's a bunch of ways for us to proceed with all this. But trig identities are very important in allowing us to handle calculus easier.